In this lecture, we will study another sorting technique in data structure, and that is quick sort. Like merge sort, quick sort also uses divide and conquer strategy. In divide and conquer strategy, we go on dividing the unsorted array into left and right sublist on the basis of some conditions, and we continue this process of dividing into left and right sublist until we get a single element in each of the left and right sublists. And for this purpose, we select an element from the unsorted array, and that element partitions our unsorted array into left and right sublists. And this element which partitions our array is called as pivot element. This pivot element partitions the array into two halves in such a way that the elements in the left subarray are less than and the elements in the right subarray are greater than the partitioning element. Partitioning element means the pivot element. Okay, and the two subarrays are sorted separately. Okay, for example, we have an array like this. So in total, we have 8 elements in this array, and what we do, we select a pivot element. For example, we select a pivot element, the last element of the array. You can select any element. You can either select this first element, or you can select any of the elements in this unsorted array as pivot element. And then by executing the quick sort algorithm, we come to a conclusion that we place this pivot element somewhere in the unsorted array. Okay, we place this pivot element suppose at this position after first iteration of this quick sort algorithm, and obviously there are some conditions on the basis of which we will be able to place the pivot element either at this position or at this position or at this position or any of these positions that I am pointing by these red arrows. Okay, and suppose we place the pivot element at this position, that is at index 3. Fine, and this 3 is the appropriate position for this pivot element after first iteration, which means that the elements which are left to this pivot element, they are having lesser values. Lesser values means they are having values less than this pivot element, and the elements which are to the right of this pivot element, they are having greater values. So after first iteration, what we get, we see that at least one element in this unsorted list gets its appropriate position, and that is at index 3. It can be index 4, it can be index 5, it can be index 6, or any other index. It depends on the conditions that we use in our algorithm. Okay, further I would like to tell you that the procedure in this quick sort, or the algorithm of this quick sort, is recursive in nature, and the base criteria of this recursive procedure is that we have to partition the unsorted array. Okay, so partitioning algorithm is the fundamental of this quick sort algorithm. Fine, this is the result of first iteration. After that, we have left sublist and we have right sublist, which means that the elements to the left of this pivot element, they create left sublist, and the elements to the right of this pivot element, they create right sublist. Fine, and as I said that this procedure is recursive in nature, then you can start with the left sublist, which is having these three elements: 1, 2, and 3, that is from 0 to 2. Fine, and now in this sublist we will choose pivot element at index 2, because the last element of left sublist is 2, and then by executing second iteration you will get this pivot element may be placed here at position 1. Okay, so what we see, we have another left sublist here and another right sublist. Okay, and in these two sublists, we find that there is single element at this position and single element at this position in these left and right sublist. Similarly, from this right side, that is from index 4 to 7, okay, we have 1, 2, 3, and 4 elements, and again we will choose the pivot element at this position, at that means at index 7. Fine. And after uh, the first pass, after calling the quick sort algorithm again in a recursive manner, we may find that this pivot element may go to position 5, or it can go to any position. It can either remain at its previous original position, that is at index 7, or it can go to position 6, 5, or 4. It can go to any position. It depends on the algorithm that we will talk later. Okay. And what we see here, when this pivot element comes here, we see in this left sublist having only one element, and in the right sublist we have two elements, that is at this position at index 6 and at index 7. Then again in this recursive algorithm again called, and what we see again, the pivot element, for example this time it is denoted by p, and at position 7, this is this can either be placed at its original position, that is here in the index 7, or it can be moved to the position 6 depending on the some conditions. Fine. And again what we get, single element in the left sublist and in the right sublist. So that is our purpose, that we have to divide, or we have to partition the unsorted array into left and right sublists, and we go on repeating this procedure until we get single element in the left and right subarray. Fine. And then we sort these elements. So the basic criteria of this quick sort algorithm is the partitioning algorithm. Okay. And one thing here I want to mention, that when we partition the unsorted array using that pivot element, it is not necessary that we will get equal halves, like the elements in the left sublist and the elements in the right sublist are equal. It is not necessary. It may happen, but it is not necessary. Sometimes in the left sublist the elements will be more, and in the right sublist the elements will be less, or vice versa you can say. But it is not necessary the elements in left and right sublist will be equal. It can be equal, but it is not necessary. But in case of merge sort, we were sure that we were finding the midpoint of the unsorted array, and on the left and right side you were expecting equal number of elements, but in this case it is not always possible. Okay. And we will take an example, and we will go through that example how this algorithm works. Now we will take an example of unsorted array, and we will examine how this algorithm actually works. Suppose we have an unsorted array like this. Suppose we select this last element as the pivot element. This is our pivot element. Fine. And in order to place this pivot element after first iteration of our algorithm at its appropriate place, that is in the sorted list, so for that purpose we have to take two more variables which are given as j and I. Okay. J is the variable that is pointing to the first element of the array, and I is the variable that is pointing to one position less than the j pointing to. Okay, that is I is pointing to a position that is represented by j minus 1. Fine. And in this algorithm what we do is we start scanning all these unsorted elements from left to right until we reach to a position less than pivot element. Fine. That is up to index 6, and we do a comparison of all the values which are pointed by j with this pivot element. Fine. So when we start scanning from the left to right, when we find the element pointed by j is less than the pivot element, in that case we increment I, and then we exchange the contents pointed by I and j. Fine. You again listen this carefully. We start from left to right scanning the unsorted array, then we compare the contents pointed by j with the pivot element, and if we find the contents pointed by j are less than the pivot element. In that case we increment I, and then we exchange the contents of I and j. Okay, and if we find the contents pointed by j are greater than the pivot element, we simply increment j and we do not go for any kind of exchange. Fine. And in this way we proceed, and when we reach to this point, that is up to index 6, there our loop ends. And after that what we do is we exchange the pivot element and the element pointed by the value of I plus 1. Okay, now let's start doing this and you will see how this algorithm actually works. First of all, what we have a of j equal to 8. Fine. Here we see a of j equal to 8, and we compare this a of j, that is we compare 8 with 5, and we see 8 is greater than 5. We do nothing and we simply increment j. Okay, now j is pointing to first index, one index. Okay, and j is no more pointing to this location. Fine. After that what we do is we again compare the contents pointed by j, that is 7 is compared with 5. Here we see 7 is greater than 5. Again we do nothing and we just increment j. Okay, now j is pointing to this position. Fine. Again a comparison is made between the contents pointed by j and the pivot element. Fine. Now we see that 2 is less than 5. So here what we have to do is we have to increment I is equal to I plus 1, which means that now I will point to this position. Okay, and I will rub this. And after that in our algorithm what we do is we exchange the contents pointed by these I and j. Okay, after exchanging what we will get here 2, and in the position of 2 we are going to get 8. Okay, and then what we do is we again increment j, so j will point to next element, that is at its position 3, and j is no more pointing to this position. Now let me wrap this. Fine. Again a comparison is made between the contents pointed by j and the pivot element. What we see, 9 is greater than 5, so we have to do nothing. We simply increment j. Fine. When we increment j, now j will be pointing this position. Okay, and j is no more pointing to this position. Fine. And again a comparison between the contents pointed by j is made with the pivot element. We see the contents pointed by j are greater than 5. Fine. In that case what we will do is we do nothing and we simply increment j. So now j will point to this position. Okay, and after that we again compare the contents pointed by j with the pivot element. We again find that this is greater than the pivot element. We do nothing and now j will be pointing the next element, so j will be pointing to this position. Fine. And then what we see that again 6 is greater than 5. We have to do nothing, but now the loop ends here. We have to exit from this loop, and then what we do is we have to exchange the contents of I plus 1 and the pivot element. Fine. Which means that take we have to exchange I plus 1, the a of I plus 1 and a of pivot or a of end. So in that case 7 will go to this position and 5 will come to this position. Fine. And after that what we will have 5 here and 7 will go here. This is our first iteration. Here our first iteration completes, and what we do is we return a value from this function as I plus 1. which means that we are returning this index 1, okay, after executing first iteration. Fine. And after first iteration, you will find that this pivot element 5, it has divided our array into two parts, okay, although they are not equal parts, but it has divided into two parts as left and right sublist. This is the left sublist, and from this point to the end, it is right sublist. Fine. And you can see that after first iteration, at least one element, that is the pivot element which we had chosen initially, that is 5, it is placed at its appropriate place, which means that it has lesser values to its left and it has all the greater values to its right. Fine. So after first iteration, what we have seen that the element which was the pivot element that was chosen initially, it has come to its appropriate position after first iteration. Fine. Now whatever we have to do is we have to sort the elements to the right of this pivot element, because to the left of this pivot element only single element was there and it is sorted. So you can see that the index 0 and 1 are already sorted. Fine. Now I will write the algorithm. We will take another example and we will examine. You will see the how this algorithm actually works. Now this is the partitioning function that I have written here, and this function can be called from the quick sort algorithm. And we will see, as I said, that this partition function is the backbone of this quick sort algorithm. So we will see how this partitioning algorithm will work on some unsorted array. We take an example of an unsorted array, and what we do is, first of all, this is an unsorted array, and when this partition function is called, we pass the array to this function as indicated here in the argument. And also there are two variables, beginning and end, beg, big and end. This is the first and the last index of your array that is also passed as an argument to this function. And in this function, what we do is we take some variables and we declare them as integer variables like I, j, pivot and temp. These are all variables of type integer, and we assign a value that is pointed by a of end to this pivot variable. Okay, pivot is equal to 6. Fine. So pivot is here. Okay, and I is equal to beginning minus 1. Fine. Beginning is 0. We have big is equal to 0, and we know that big equal to 0, and I will be 0 minus 1, which means it is equal to minus 1. So I is equal to minus 1. We are initializing the j loop here. J is equal to big, which means that j is equal to 0. J is less than end, so j will run up to this position, that is up to index 6. Fine. And is 7 in our case, and equal to 7. And we check here a condition at this point. If a of j is less than pivot, a of j means a of 0 is less than pivot. Is 8 less than pivot, that is 6? No, it is wrong. So this condition will not work. All these statements will not work. Okay. And we again go up and we increment j. So j will be incremented, and now j will become 1. And then again we check if a of j, which means that a of 1, that is this element, if it is less than pivot element, yes, 2 is less than 6. In that case, what we will do is we have to increment I. Now I is incremented, So value of I is 0. And then what we are doing here, we are exchanging the contents pointed by I and j. Fine. So our j is pointing to a of 1 and I is pointing to a of 0. Fine. So we have to exchange 2 and 8. So after that 2 will go to this place, 2 will come to this place, and 8 will go here. Now I is at this position and j is at this position. And then what we do is we again increment j. We have to increment j, we go back and we come to this point, we increment j. Now value of j is 2. So j is pointing to new location. J is pointing this position. Okay, j is 2. Then we see if a of j is less than pivot. If a of j means if 5 is less than 6, yes, it is true, then we have to increment I. So now we have to increment I. I will become 1 and here I will also be incremented. Now I will be pointing this index. And what we have to do next, we have to exchange the contents of I and j. That means the contents pointed by I and j. So we have to exchange 5 and 8. When we exchange 5 and 8, we get the array like this. So here what we see when we go on tracking from left to right, we see the contents pointed by I and to the left of I are less than or equal to the pivot element. Fine. That is the main thing that we have to keep in mind while we design the algorithm. Okay. And after that, what we do is we again increment j. So j is again incremented and now j will be pointing this location. Okay. Is if a of j by this statement. Okay. If a of j is less than pivot, a of j is 3, yes, it is less than 6, then all these statements will work. That means we have to increment I. So I will be incremented. Now I will point this location and I will be incremented as 2 and I is no more pointing to this location, and we have to exchange the contents of I and j. J was already incremented as 3. Fine. We have to exchange the contents of I and j. That means we have to exchange 8 and 3. So after exchanging, 8 will go at this location and 3 will come to this location. Again you see the contents pointed by I and to the left of I are less than or equal to 6. Okay, that is the main thing we keep in mind. Fine. And again we come out of this loop and the j will be incremented as 4. Okay, now j is pointing to next location, that is 4, and j is no more pointing to this location. Fine. Again we compare the contents of j and the pivot element. We see the contents of j are greater than the pivot element, we simply increment j. Now j is pointing to location 5. Fine. We compare the contents pointed by j with 6. If a of j is less than 6, no, it is greater than, and we again increment j. Now j becomes 6 and j will point this location. Okay, and we will remove this. Now j is pointing to 6. We again come to this point. Is j less than end? Yes, this condition is true. J is less than, and j is having value 6, it is less than 7. And then we will see if a of j is less than pivot. If a of j, if 20 is less than 6, no, it is wrong. We will come out of this and again j will be incremented. Now j will become 7. So j will be pointing to next location, that is this. Now j and pivot are pointing to the same location. Okay, and now we will check this condition. Is j less than and? No, this is not true. We will come out of this for loop. We come out of this for loop and we will reach to this place. Now we are here exchanging the contents which are pointed by a of and. What is and? And is having value 7. A of 7 is 6. We have to exchange the contents of 6, contents of a of and, that is 6, with what we are exchanging. We are exchanging contents with the a of I plus 1 location. Now I is this, I plus 1 location is this. So what we are going to do is we are exchanging the contents pointed by I plus 1, that is this location, and the contents pointed by a of and. So 8 and 6 will be exchanged. So after exchanging, 6 will come here and 8 will go to last index to this place. Now after first iteration, what we see that we had chosen 6 as pivot element. 6 was our last element in the unsorted array, and now after first iteration 6 has been placed to its appropriate place in the final sorted array. This is not the final sorted array, but the location or the place for 6 will be this one only. So you can see that the contents or the element to the left of 6 are less than or equal to 6, and to the right of this 6 they are greater than this 6. So we can say that 6 has been placed to its appropriate place after first iteration. Similarly, now we have two lists because we are returning the value I plus 1. I plus 1 means we are returning the value 3 in this case. Okay, so this partition function is returning the value 3. Fine. Now what we have to do is we have left sublist that is indexed from 0 to 2. Okay, this is the left sublist. Fine. And now we have the right sublist. This one is the right sublist. Again, what we have to do is we have to call the this quick sort algorithm again, and again the partitioning will be done on the left sublist and on the right sublist. Again, in the left sublist we will choose this 3 as pivot element. Okay, and this 8 as a pivot element in the right sublist. And similarly, by executing all these statements all in this partition function, we will place 3 and 8 at their appropriate place. Fine. And after that we will again get left and right sublist, and we will repeat this procedure until we get single element in each of the left and right sublist. Fine. And as I said that this procedure is recursive, and we have to see how the this quick sort algorithm calls all these functions recursively, and either it can call to itself and also it will call to partition function. Now let me write the quick sort algorithm. Now this is the quick sort algorithm. Here we see that we are passing the arguments as array, and the initial index as beginning and the final index as end of the array. Okay, and we see that we are taking here another variable that is denoted by loc, which is denoting location actually. And we check here condition. This condition is just to execute our loop when our initial index is less than the final index. That is, if beginning is less than end, only then all these things will work. Fine. And this also indicates that there are at least two elements in the list for which we are going to call certain functions under this. So at least two elements has to be there where we have to take the comparison. So for that purpose we are taking it as beginning is less than end. Fine. Then we are calling the partition function here. Okay. And whatever is returned from that function, that will be stored in loc variable. Fine. We have just seen the partition function before this, and where there we were returning the value as I plus 1. Okay. That will go to location variable. Fine. That value is basically the position of the pivot element after placing the pivot element at its appropriate place. Fine. In our previous case we got the value as 3, and then this function recursively calls itself, and now we are passing parameters here as a, that is the base address of the array, and beginning, that is the first element of that unsorted array, and location minus 1 as the end. Fine. Why location minus 1? Because up to location, the element at location is placed at its appropriate place. Now we have left sublist, and that is from beginning to location minus 1. Fine. We have to partition that list only. Then in the next call, that is again to the function calls itself, again we are passing the base address of the array, and we are giving the first start index as location plus 1, which means that the element next to the pivot element after placing at appropriate place. Fine. That is location plus 1, that is the right sublist. The initial index is starting from the location plus 1 for the right sublist and up to end. Fine. So we have right and left sublists, and we have to partition them until we get single element in each of the list. That is what we are doing in this particular function. From this partition algorithm, what we have seen that after first iteration, it returns a value 3, which means that the index 3, which indicates that the pivot element is placed at its appropriate place, that is index 3. Okay. And now when we go ahead and again when the function calls itself, okay, let me write the same array here. After first iteration, what we got this array. We got 6 at this place because we had chosen this as pivot element, and the rest of the elements are placed like this: 2, 5, 3, 11, 9, 20, and 8. This we have already seen in the previous case, and now the element that we had chosen as pivot, it is placed at index 3, and now index 3, and we have returned in that function the value 3. Again, when we call this function quick sort, in this case now the array a beginning is the index 0. Okay. Location minus 1, location is having value that is 3. Okay, 3. So here now the left sublist will be from 0 to 2, location minus 1, location is 3. Okay. And the right sublist will be from location plus 1, location plus 1 means 4. Okay. To 7. This is the left sublist, and this is the right sublist after first iteration. Now when this partition function is called for the very first time here, what we get is, before that, we had already called quicksort algorithm in the main function by providing beginning and end as the initial and last index of our unsorted array, and then we check here if beginning is less than end, then we proceed. So first the call to this quicksort function goes like this: quicksort from index 0 to 7 in our case. Okay, we have 8 elements, and after first iteration, when we call the function, this partition function calls is being called here, and this partition function is denoted by p, that is from 0 to 7, and this function returns a value 3 as shown above, and this partition function returns a value 3, the index 3. Okay. and then we again call quick sort recursively, and this call depends on the returned value that is stored in the location, and here we have 3. Okay, so here we have to call this function quick sort again as quick sort, that will be having the index from 0 to location minus 1, that is 2. And similarly next call, that is this one, quick sort a location plus 1. So third call would be like this, quick sort and location plus 1, that is from 4 to 7 to end. After calling this quick sort from 0 to 2, when we call from 0 to 2, then this will again call the partition function. Partition function will be called from 0 to 2 like this, partition 0 to 2 from this point to this point. Okay, and now we choose pivot element. This is our pivot element. Okay, and again we take two variables I and j. I is pointing one position less to j, and j is pointing to first position, to this position. Okay, and I is pointing here. Fine, what we do is we compare the contents pointed by j. J is pointing to 2. 2 is less than 3. Yes, 2 is less than 3. What we do, we increment I and we exchange contents of I and j. So I is incremented and it points to this location only. So I and j are pointing to the same location, so 2 will remain at its original position. Then we increment j. Now j is pointing this position. Fine, and j is no more pointing this position. And what we do is we again do the comparison, and here we see 5 is greater than 3. We do nothing and we increment j. Now j is pointing to next position, and here this tracking of elements ends, and what we do next is we exchange the contents pointed by I plus 1 location with the pivot element. So I plus 1 location is this one. Okay, what we do is we exchange these contents. So after that 3 will come to this place and 5 will go to index 2. So after that this pivot element has been placed at its appropriate place. Fine, and what will be returned after this, that's I plus 1. Fine, so it is going to return I is 0 and I plus 1 is 1, so this is going to return 1. And again the next call from this depends on the value of this 1. Now further, quick sort algorithm will be called as quick sort. It is based on the this value that is returned from the partition function, beginning to location minus 1. What is beginning? 0. What is location? 1. 1 minus 1, 0. Also another quick sort call will be made, that is location plus 1, that is from 2 to end is 2 only. So what we can see from this point, nothing will happen here and nothing will happen here, because we have single element here and we have single element here also. So when we have single element in the sub list, then we consider that list as a sorted one. Now when we go to next step, here the quick sort call is from 4 to 7. Okay, now the right sub list is from this point to this point. Fine, again the partition function will be called, we call the partition function as this p from 4 to 7. First we check, is p is beginning less than and yes, 4 is less than 7. Then we call quick sort algorithm. Okay, quick sort algorithm is called, but it depends on some value that will be returned by this function. So in this case what we do is we select this 8 as pivot element. This is selected as pivot element, and we take I and j values. J is pointing this position and I is pointing this position. Okay, and what we do is we go on comparing the element pointed by j with the pivot element. Fine. Here element pointed by j is 11. 11 is greater than 8. We do nothing, we simply increment j. So j is pointing to this, and j is no more pointing to previous value. Fine. Then what we do is we again compare the contents of j and pivot element. Here we see 9 is greater than j. We do nothing and we simply increment j. Now j is pointing to this element and we will omit this. Fine. Again we do a comparison, and we find that j is pointing to 20 and 20 is greater than 8. So nothing will happen and j will be incremented, and now j will point to the same element, that is pivot element. Fine. Here loop will end, and what we do next is we exchange the contents at location I plus 1 with the pivot element. So after that what will happen, 8 will come to this position. Okay, now we will write 8 here, and what was there, 11 was there, and 11 will go to this position. 11 will go to this position. Fine. And now what we return after completing the job of partition function, what we return I plus 1. So here 4 will be returned by this partition function. Now next list will be from beginning to location minus 1. Beginning was 4 in this case, and location minus 1 is 3. Fine. And next call to the quick sort will be from quick sort location plus 1, that is 5 to 7 end. Okay, when we see this call, nothing will happen because here beginning is greater than end, so this will not be executed and our program will stop here. And what we see in the next call, again the partitioning algorithm. Now the list, that is the right sub list here, is from 5 to 7. Now we have a new list that we have to sort, and that starts from this place, from index 5 to 7. And what will happen here, again this quick sort function will call the partition function. Okay, again the partition function will be called from 5 to 7. And what will happen here, again we will select this last element as the pivot element, and I and j will be pointing to this place, and I will be pointing to previous place. I is pointing to index 4 and j is pointing to index 5. Fine. What we do is we compare contents of contents pointed by j with the pivot element. Here contents pointed by j are less than the pivot element. What we do is we increment I and we exchange the contents of I and j. So first we will increment I. Now I will be pointing to the same position as the j is pointing, and I is no more pointing to this previous position, and we have to exchange I contents pointed by I and j. So 9 will remain here only. Fine. And then we increment j, and we will remove this j pointing to the previous position. Now j is having contents as 20, and 20 is greater than 11, so nothing will happen, we just increment j, and now j is pointing to this pivot element and j is no more pointing to this. Fine. Here our loop will stop working. Okay, and next step what we have to do is we have to exchange the contents pointed by I plus 1 location, that is this location, with the contents pointed by the pivot element. That means we have to exchange 11 and 20. So we have to exchange 11 and 20. So after exchange, 11 will come here and 20 will go to this place. And what is returned from this function? value 6, that is I plus 1. I is pointing to 5, I plus 1 will be returned. So next quick sort call will depend on this value. So here quick sort, that is from beginning to location minus 1. What is beginning? Here beginning is 6, location minus 1, location is 6, and location minus 1 is 5. Okay, and the other quick sort call will be from location plus 1, that is 6 plus 1, 7, to end 7 to 7. Here we see that single element is there, nothing will happen further. And also here the initial index is greater than the final index, last index, so nothing will happen, this will not be executed. So this is how the function calls will work in our quick sort algorithm. This is all based on this quicksort algorithm. Now we shall see the analysis of this quicksort algorithm in terms of time complexity. When we call partition algorithm, we have n minus 1 comparisons, and the complexity or the time complexity for that is big O of n. And suppose for the best case scenario, the partitioning element partitions the unsorted array into two equal halves. That means the elements in the left and right sub arrays, they are equal. In that case, then we can have log n splits. Okay, then we can write this function, that is a quick sort function f n is equal to n, that is n comparison into log n. Okay, so the time complexity will be denoted as big O of n log n. Okay, but it is not always possible that we will get equal number of hobs after partitioning the unsorted array. So the worst case scenario may have big O of n square as time complexity. Okay, so this is all in this algorithm. Now we shall see the implementation of this quick sort algorithm. I have written a program in C language. Now let us see that program by executing that program in the compiler. Here I have written this program in C language for quicksort, and first we will start from this main function. Here is the main function of this program, and I'm taking two variables I and n, and I is taken as the variable to control the loop, and n is taken as for array size what we want to give. So I'm scanning this n here, and here I am declaring an array of size n, and after that we are scanning the elements of our unsorted array here, and then we call the quicksort algorithm or the quicksort function. Here we are passing the arguments as the array a 0, that is the initial index, and n minus 1. Okay, when we are starting the index from 0, then we will go up to n minus 1, and then this statement calls the function quicksort, and whatever is done in this quicksort function, after that we print the array, and here we are printing the sorted array by using the function call print array. Okay, and there we are passing the base address of the array and the size of that array. Okay, but before that we are calling this quicksort function. Fine, so we will go to quicksort function. Here we have written the quicksort function. This is the quicksort function, and it takes the arguments as the array beginning is having value 0, and end is having value n, the size of the array. Okay, here we are declaring another variable, that is location, which we are considering to store the value that is returned from the partition function. Fine, and we check here if beginning is less than end, which means that if the initial index of the array is less than the final index, only in that case we will proceed and execute all these statements. If this is not true, that is if beginning is not less than end, in that case we come out of the loop. That means there is not a valid input array. Fine. And we call here the partition function, and whatever returned from that partition function is stored in the location. And when we call this partition function, it takes the array a, beginning and end variables. Okay, now we have to go to partition function. This is the same function that we have seen, and I have written here. This partitions our unsorted array into two parts. Fine. And it returns the location I plus 1. And this location further decides the next call, that is quick sort, from which point, that is from beginning to location minus 1. And again another call is done on the right sublist, that is from location plus 1 to end. As this function is a recursive in nature, so this will go on calling itself again and again until it gives us right and left sublists having single element only. After doing all this, the next call in the main function is to print the elements of array. Okay, now this we have sorted elements and we have to print. We print those elements by calling this print array function that I have written here, and this function takes the argument as the base address of array and also the size of array. And here we again take this variable I as the variable to control the loop. Here you can see we have taken for loop and then we print the array. Now let me compile this program. Here we have this execute button. Let me compile this. You can either use F9 or this compile button. You can see that there are no errors and warnings in this program, and then we run or execute. You can also run it by pressing F10. Okay, it is asking me to enter the size of array. Suppose we enter the size of array as 8. Fine. Now enter 8 elements of array. First element I enter 9, then 5, then 7, 0, again 9, okay, 0, 2, and 77. One more, 8, 6. Now you can see we have the sorted array as 0, 2, 5, 7, 9, 9, 77, and 86. Fine. You can give any other size of array and you can have the sorted array by using this quicksort algorithm. I hope you people have understood how this quicksort algorithm works. So this is all for this lecture. Thank you for watching.